Hello everyone, welcome back to the class, and today we're going to cover topic 12, collapse strengths of the column, and this is the last topics for the column methods. So basically we have learned about the elastic buckling column and produced by the Euler equations and different boundary condition effect. And last time you remember that the effective length concept and how we're going to utilize the Euler buckling equations, how we're gonna calculate it, how we're gonna drive all the formulations, and today it will be more practical and how the shipyard and designer engineers they utilize the design formulations as well as the empirical formulas, something like that. So here the main topic, main objective will be the buckling strengths and how to consider all those details, imperfections, his centering load, slenderness. But all the details you'd better to read the given reading material in advance. And at the end, what I want for you to understand is that you should be able to calculate critical buckling stress of our column. Once again, why the column is important, you should remember PSC, plate stiffener combination model, like here. This is plate, this is stiffener, and our stiffened panel from our ship, that is the combination of this one, another PSC model, another PSC model. So once we connect it, then this shape will be like that. So this is similar as outer bottom, you know what I'm saying. So our stiffened panel from the ship or side shell, deck, all those things can be calculated based on this technique. So here again, we should be able to calculate critical buckling stress. That is the process of local strength analysis. So once we complete the global strength analysis, we will route that information for our local strength analysis. That information, apply the force or the stress, will be used to judge our local, buckling capacity will be good enough or not. So here we will decide column will be safe or not. So that's the thing. And the last time I think I have highlighted many times, but here the effective length concept, and LE effective length can be defined as K times L original length. This K is the coefficient for simply supported case 1.0, and one fixed, one free 2.0, and the fixed conditions 0.5, and one fixed, one pinned or simply supported, then K value was 0.7. So we simply utilize this equation to calculate PE was pi square EI over LE square. So this is the final shape to calculate this elastic buckling force. So we've seen this video very last moment. We will see this again, and they will put some steel powder and then apply the load increased so that it will be like that, and then certain point it will buckled like this. First, sorry, shoot, right, it is buckled, and then the boundary condition effect. Like this is number 1, then this is number 2. It's like that. Now you can understand what I'm talking about, right? So please have a look this video by clicking this link. We discussed many times about the load carrying capacity, as well as the importance of the boundary conditions and the failure shape, What I mean is the buckling shape and effective length K. So that's almost everything. And a few more details will be introduced by topic 12 now. So where we are, from the obtained equations, Euler buckling formulations, we could be able to plot this graph, which is the relationship between inelastic buckling stress E over yield, material yield. So this is the ratio. So 1 means it reached yield strength, isn't it? So this is column slenderness ratio, and I would suggest you to remember this. So this is slender region, this is stocky, this is intermediate, and this straight line, this line represent Euler formulations. And actually there are a few more formulations, design formulations, Ferry-Robertson and Johnson-Ostenfeld and something like that. So I will introduce it later. And then the last time we discussed about the initial imperfection, initial deflection. If we don't have any, defect, then it will behave like this way, up and to the right. But if we have initial deflection, we will start from here and it will be deflected like that, right? So the factor influencing the buckling strength, this might be important for us to, see the overall figure. So initial deflection, initial imperfection, residual stress due to the welding, and inelastic effect, and load eccentricity, local buckling methods. All those things will affect our buckling strength of our column or our structure. And how are we gonna take into all those factors and uncertainties? This is truly important for us. So we can simply, one of the approaches, this is pretty much simpler. The first approach is just put it here. As you can see here, one simple factor we call the reduction factor should reflect the factors of influence due to the uncertainties. You know what I'm saying? So in other words, we can modify our equations like here. This is used in reality. So that's why I'm asking you to remember this. So elastic buckling strength, and we call critical buckling strength. So in this case, what I'm talking about is once we calculate elastic buckling strength, and then we can modify it to get critical buckling. Of course, might be better than critical buckling. You know what I'm saying? So we need one more step to get this one. For modifications, I will introduce it soon. And then we need to remember what was lambda, that was column slenderness ratio, right? But anyhow, what we need is, this is lambda, this is stress over yield. So based on this, we want to predict, once we decide our, column, like this is plate and stiffener, the combination model, we can select the stiffener shape, flat or the T or angle is up to us. Once we decide our geometry, then we can simply calculate, this is function of geometry as well as material properties. So this one, the column slenderness ratio, can be decided, and then based on these formulations, E and critical buckling, I will introduce it soon, so that we can decide this value. So step is like that. This one, check material properties, geometric properties, and then substitute it to here so that we can calculate column slenderness ratio, and then use the Euler buckling stress so that we can get stress E and then modification, critical. Now we are here. How are we gonna do this? Okay. So the yielding effect, and actually especially this region, intermediate elastic plastic, or we call the elastoplastic buckling, interaction between the yielding and the elastic buckling region here. So this part represent yielding is dominant, especially here in stocky column case, and if the column is slender, that is governed by elastic buckling, this is dominant. But here, intermediate case, we need to consider elastoplastic buckling, the interaction between yielding and elastic buckling. So that is reason why the next slide here, Rankine-Gordon interaction curve, they try to consider different yielding and elastic buckling strengths. They just simply add up. And then they define that, okay, this is our critical buckling strengths. So what we need is actually here elastic buckling strengths, this equation from the Euler buckling formula, and this has been already defined, and lambda is column slenderness ratio. So just simply brought it here, this one, 1 over lambda square times yield is here, and yield, so that we can simplify this again. So the equation will be, simplified again. So this is the Rankine-Gordon interaction curve, and this is the outcome. So as you can see here, this is proposed by the at all time the best way to explain the formula, explain the graph is show the relationship between the horizontal and vertical axis. So this shows the what we call the column slenderness ratio here, and the vertical axis is critical buckling strength. So previously we have obtained these Euler formulations that is here, and at the same time just now we have learned about Rankine-Gordon formulations. So actually, as you can see here, this one proposed by Euler, this is overestimate, and Rankine-Gordon is underrate. And reality, this is come from the real, testing experimental data. You can see the range, you know what I'm saying? So it's up to us. We can put some safety margin by, applying by using this Rankine-Gordon formula or Euler formulations. That is our engineer's judgment. You know what I'm saying? So, but a few more things I'd like to introduce it. You can have a look if you want. I will upload all the detailed the journal papers, and this is like the existing empirical formulations. As I explained earlier, this PSC, this is come from the column, but this stiffened panel can also be predicted by PSC or these kind of formulations, right? So compression case, and the other one is also like empirical formulation for flat type stiffened panel or T type stiffened panel empirical formulations. You can assess it. And inelastic effect, what they are talking about is here, like this region, tangential modulus, like in all the formulations. So reconsider the stress and strain curve. As you can see here, we have the proportional limit, and then our stress strain curve will be changed like this, and then we will experience yielding. We have this kind of tangential modulus, and Johnson-Ostenfeld formulations, if the proportional limit is 0.5 times yield, half of yield, then he suggests that, okay, we'd better to utilize this one. So basically, Johnson-Ostenfeld and previous formulations, everything is connected, but all the detailed derivation, you can find the lecture note, but this is practically used in real shipyard. That's why I'm asking you to remember this slide. So the way is PE. Number one, elastic buckling strength. Number two, and then it can be converted to critical buckling strength. Sometimes it will be same as elastic buckling. Sometimes it will be changed, modified like that. So there is a criteria based on the geometry, based on the lambda. So here we will explain it further soon. So about these formulations, Johnson-Ostenfeld formulations, which is actually used in the shipyard. So as you can see here, Johnson-Ostenfeld formulations, it looks quite simple, but yet accurate. As I explained earlier, we've learned about the Euler formulations here, as you see here. And at the same time, we can see the Rankine-Gordon formulations, blue line, and actually the dot here, this represented testing data from the experiment. So like just now we learned about the Johnson-Ostenfeld formulations that is shown in here at the center, like in between those two lines, Johnson-Parabola and Johnson-Ostenfeld. So what they want to talk is these might be considered as more realistic formulations, but basically, as you can see here, that should be done by our we engineers' judgment. So one more thing is, as you see here, this kind of testing result, even we select the stiffened panels or the columns geometry as well as material modeling, then we can get column slenderness ratio. As column slenderness ratio increased by the stress value is decreasing by predicted by empirical formula like design formula, Euler formulations, and Rankine-Gordon or Johnson parabola. But what I mean here is you can see this testing result is not constant. What I'm saying is this is like fluctuating behavior. So this kind of single line shape formulations might not be able to predict accurate result. That is reason why, like here, this is one of the recent publications. You can click the link here, and here empirical formulation developed by this is shown in here as a shape of this triangle, red color, and ANSYS, which is one of the famous finite element method numerical simulations. So that is shown in here. So all those things, all the formulations, Perry-Levertson, Johnson-Ostenfeld, as well as existing, other formulations, this is all like a single line formulations, but it was not able to predict the accurate values. That was reason why they produced the advanced empirical formulations to predict this kind of nonlinear behavior by data processing. So that's for your information. And again, Johnson-Ostenfeld formulations we've highlighted many times, and this is used in the classification societies such as the Lloyd Register, ABS, Korean Register, something like that. But basically, how we can understand this formula is here. Step 1, we need to know how to calculate Euler formula, Euler buckling stress. So we can simply utilize that equation so that we can calculate this first. And step 2 is modify. And the question is how. One of the way is shown in here. So what is the purpose? We want to get critical buckling strength. This was elastic, and now we are talking about critical, right? So that represented by stress CR, and you can see here if this is lambda, this is stress over yield, and if the obtained stress value here, and this is 1.0, meaning that the obtained stress value is approaching the yield stress. That's why they put the ratio is 1.0. So if the obtained value is plotted in this area, this is actually 0.5. So in between, above 0.5, this region, then we need to consider to modify our result. But if the obtained value is less than 0.5 yield, like here, we don't need to take any actions. So obtained value, this stress E will be considered as critical stress. This is one. If here, this range, then we need to apply this equation. It's not difficult. As you can see here, elastic buckling strength, bring it, substitute here, and yield stress. So physical meaning is yield stress times certain value to consider degradation. So it will be adjusted slightly. So that will be considered as critical buckling strength. You know what I'm saying? So here, this is another, existing formulations used in the shipyard, effect of imperfections. So we call the Paik-Thayamballi Formula. At the same time, we can see here, this is the midship section, one single sliced model for the oil tanker, the deck or the inner bottom, outer bottom. Here, once again, the main thing is column, like this. Until now, we continuously discussed about this matter subjected to the axial compression, but this can be extended by adding additional, columns here, so that it will be like that. This one, like plate stiffener combination model, we call PSC. This is one PSC model. So attach it few more so that it will be like stiffened panel. So exactly same way we can check local strengths, or here critical buckling strengths for column or stiffened panel can be calculated. So this is quite interesting topic. And once we apply the axial compression to our, stiffened panel, it will be buckled like this. And from here, we can obtain critical buckling strengths. So in the case of critical buckling, for your information, if the structure is 1D, like column, and if the structure is like 2D or 3D, like plate or stiffened panel, then what is the difference? In this case, these obtained critical strengths can be considered as the ultimate strengths, but in the case of these plate 2D or higher 3D, might be ultimate or might not be as well, because here this is the combination of fiber here, so it will interact each other, so it will not be same in general. So another empirical formulations existing, Paik and Thayamballi, if I'm not mistaken, they proposed these formulations in 1997 by the conference. So make it simple. This is the function of lambda and beta. Lambda is column slenderness ratio. Beta, I think this is the first time that you are, seeing this formula. It's simple. So in the case of beta, this is plate breadth, width B, and the thickness of the plate is T. So beta is B over T, loose square, material properties, yield over elastic modulus. So based on this, we also have the stiffener and another plate. So how to calculate this lambda? Please don't be confused. This is continued plate, and we have stiffener. We have to cut it at here at the center. So this will be the plate width B, and this, like this one, will be used for the calculation of lambda, and this one plate will be used for the beta. Sometimes the student, they select this one, like this one, and then calculate lambda and beta. Of course, that's wrong. Okay. So here, Paik-Thayamballi Formula, they have changed the beta, and they've seen compared with the Perry-Robertson, something like that. At the same time, we can ask which formula you would prefer when designing one-dimensional 1D member subjected to the axial compression. Of course, we have the Rankine-Gordon or Johnson-Ostenfeld, Perry-Robertson, or existing Paik-Thayamballi Formula. At the same time, I have introduced few more existing empirical formulas. I'd like to recommend you to check this paper. You can see few furthermore empirical formulations as well as design formulas, and they have compared the accuracy as well. So one simple example, if let's say they are asking us to calculate critical buckling strength, and the given information is here: diameter 1.2 meter, thickness 16 millimeter, length 20 meter, and the material properties here: elastic modulus, gigapascal. Please, I do believe that you are familiar with the unit, and yield strength 340 megapascal, looks like high tensile steel, and nicely they provide the formula to calculate the moment of inertia for this tubular member. It will be like this shape, and I calculation given, and the support condition at the end, simply supported or pin column subjected to axial compression in it. So based on the given information, we can calculate moment of inertia and sectional area, and R was I over A root square. We can simply calculate it based on these informations. So based on these, we can calculate this column slenderness ratio. Why we need to do this? Because most of the formulations, this is column slenderness ratio, this is the target value, in this case critical buckling strength. So first step is we need to calculate the column slenderness ratio here. So that is 0.604, 0.604, and then we need to select the function. The existing functions is up to us, and then once we select single function, for example here, then move up, then read this information. That will be the outcome, right? So if you use the Euler formulations, the value will be 2.743. It is quite, interesting outcome, because here the value equal to 1.0 means yield. 2.7 means 2.743 times yield. So which means that, for example, yield was 340 times around 3, that is about 1000 megapascal. So this is actually not the, realistic value. You should understand the meaning of this, obtained value. So if we adopt the Rankine-Gordon formula, we could be able to obtain 0.733, Johnson parabola 0.9 something. And if you adopt Paik-Thayamballi or the other formulations, empirical formulations, you could be able to obtain critical buckling strength as well, or sometimes they use ultimate strength. Now you can understand what I'm talking about. So another example, exactly same, sectional properties, lengths, and material properties, everything given. And one thing is they ask us to use Johnson parabola formulations and check the critical buckling strength. So please have a look on this, try it. So reminder, from this lecture, lecture 10, topic 10 to 12, we really focused on the column buckling methods and safety assessment, critical buckling strengths. And now we are able to calculate the critical buckling strengths of the column as well as the PSC model, and it can be expanded to the stiffened panel. And actually stiffened panel is considered as a local element in our ship structures together with the plate. So we have derived all the formulations from the Euler buckling formulations, effective lengths, and boundary condition effect, and further details. So please have a look. Every details could be found in lecture note 10 to 12. And in addition, I will provide the useful the journal papers to see the existing empirical formulations and applicability studies and verification, as well as validations. So next class we will focus on the trust, and I think that's all today. Thank you very much. 감사합니다.